So good old magnesium, 282, located there on the periodic table. We turn up the voltage, take one away. That energy needed is called now the first ionization energy, the energy needed to remove one electron. And the first one comes off the easiest. If it didn't come off the easiest, it wouldn't be the first one. Because the first thing to go is always the easiest thing to go, right? You see what I'm saying? If you've got a structure that has a weak beam, if the structure fails, it's because the weakest thing failed, right? So the first one comes off the easiest. And we've just looked at that. And that's not that exciting. So the first one comes off the easiest. Excellent. We're not worried that much about the first one. We just learned about it. Now let's talk about then plucking off a second one. The second ionization energy is defined as the amount of energy to remove the second electron. In this case, there are 12 protons pulling on 11 electrons. The electrostatic force, therefore, on that valence electron is stronger, and therefore it takes more energy to remove the second electron. So the second ionization energy is greater than the third. Now, we're at our stable ion, but to continue the analysis, we're going to be evil. We're going to remove the third electron. What do you think is going to happen to the amount of energy needed now to remove the third one compared to the jump that we needed to remove the second one? Think about where we're taking that thing from. Haley, what do you think? And comparably, how much more do you think? A lot more. I like that. A lot more. Let's keep it simple. Why is it going to take a lot more? Yes. It's going to be removed from the second orbit, which is much closer to the nucleus. Therefore, the electrostatic force is much greater. And so to remove it, there's going to be a great big jump in ionization energy because now we're pulling it from the second orbit. Excellent. Good analysis. So I'll bring all this stuff up. It has everything to do with the fact that the inner orbits have such a strong hold on the electrons, reaction stops. Reaction is done. Now we're evil, and we are removing them. Here's the last bullets here. So it's this big, significant jump in ionization energy between removing the second and third that makes magnesium have a stable +2 ion. So here you can see I'm expressing the third ionization energy has a greater than the second ionization energy compared to the first ionization energy, which is why that doesn't happen under chemical situations. We can rip it off with a machine, but not in a chemical reaction. That's for magnesium, my example. If I was talking about aluminum, which ionization energy would be the big jump? Which ionization energy would it take a lot more energy to remove? Atlee? The fourth. One would fall off. Second one not fall off. Plucked away. Second one plucked away. Third one plucked away. We're back to here. Now we're back again to the second. It's going to be a lot of more energy to pluck that away. So aluminum chemically only gives up 3 because nothing can pull away that next one. Yes, I do want that written down. Sorry, there is a large jump in IE after the last valence electron has been removed. Sorry about that.